Okay, we can have also some more complex predicates that have more than one input variable. So for example, I can have a function that has two variables. So I've given you an x value and a y value, so I'd like you to plug those in and just write down the statement that results from Q32. So x equals 3, y equals 2. I want you to copy it down into the statement that Q stands for, x less than y and x squared less than y squared. And then I want you to tell me if it's true or false. Did everybody plug it in? Check it with your neighbor and see if you got the same thing. Okay, so we should have put down 3 less than 2 and 9 less than 4. This is clearly false, right? Okay. Are there any values of x or y that would make this true? Which ones? 1 and 2. So let's do Q of 1, 2. Okay, that's good. That's true. So we know that it's not always true because we found one false, right? But we know it's sometimes true because we found one that was true. How did you find the one that was true? Yeah, you. With your brain. Okay. So, but that was not very specific. How do other people use their brains to find them? What'd you say? Not the teacher. Okay. How do you figure it out? Well, the truth of the matter is that we try stuff. Okay? We read it, we think about what does this statement mean? And when could it possibly be true? If you have no idea, how do you start? Just try some numbers. What are good numbers to try? 1, 0. Why are 1 and 0 good numbers to try? All math is easier. That's why they're good numbers to try. And also 0 is often a boundary case that breaks things, right? So the next thing to try is a negative number because that often also breaks things. So if you're looking at real numbers, that's what we're looking at here, not just binary. Try 0, 1, and minus 1. If we're looking at real numbers. And then if those are all working, then start trying some large numbers and then start trying some like fractions. And then if it's true all the time, try to think about whether, like all the examples you try and you still keep trying to stump the system, then think about whether you could actually claim that this was true all the time. How often do you think we run across statements that are true all the time? Very rarely, okay? Your math book is about the only place you're going to run across statements that are true all the time, okay? Because they've actually worked really hard to figure out which things are true all the time, and then they put them in a book so people can find them, okay? Because there's so many false things in the world, all right? So all your axioms, for example, for your proofs are things that are true all the time. And if you think about it, that's still relatively a short list of things that is true all the time. Okay, so most of the time, if we ask you something like for all x, for all y, q of x, y, you don't have to use your brain like our lovely friend did. You can say, probably not. Okay? You can verify it if you have a good idea of which things make it false. Okay? We can use multiple quantifiers because we have to have a quantifier with every single variable in order to bind it to enough values so we can tell if the predicate becomes true or false. Okay, so q of x, y here actually is not bound to a variable, is it? No, but the quantifier, what a quantifier does is it counts how many. So quantifier comes from quantify. that means we're counting how many input values make the output value true. So for all actually is like writing down a little and between all the possible values, all the possible input values. So if this were true, that means that every single x value in the entire universe of real numbers and every y value in the entire universe of y numbers makes q of xy true. So I don't even want to start to write out what that actually means. It's a big and statement. So let me give you an example of what big and statement it is.